start. Oh, there we go. I will speak to this mic. Okay, let me just. There you went. Okay.
Sorry, that's.
There we go. Good. Okay, so I'm here to present the findings from the white paper. All right, I'm going to use this one instead. I'm here to present the white paper findings from the Planetary Science with Astrophysical Assets Committee. I wanted to start off by thanking the 15 committee members, very dedicated members that have dedicated a lot of hours to this study. And particularly, I'd like to thank Stephanie Malam, the co-chair, and also Doris Dow, our NASA headquarters contact, who has provided a lot of strategic and logistical suggestions. And then finally, I'd also like to thank the Small Bodies Assessment Group Committee and the chair for supporting this. Okay, what is this? Well, this is an attempt to compile a uniform set of capabilities that would facilitate solar system science using astrophysical assets while not interfering with the missions in terms of their main goals. So we prepared a white paper for the 2020 Astrophysical Decadal Survey. That'll be up on ArchiveX when just before we submit it to the Decadal Survey. The committee was comprised with a variety of different people spanning the subspecialties within planetary science, experience, and across institutions. And we've solicited input from the community through various methods, including conferences and email and web forums. So the motivation behind this is pretty obvious. Planetary science has benefited a lot from observations conducted with astrophysical assets, astrophysical telescopes. Generally, these include some of the earliest pioneering missions in terms of breaking wavelength space and such, like IRAS and COBE. Of course, the great observatories have also contributed quite a bit. And some missions like WISE and projects like PanSTARRS have evolved from primarily astrophysical missions into primarily planetary science missions. So this, though, is not a one-way benefit. It also goes the other way. Small dedication of time, even marginal dedications of time on the order of a few percent, yield a lot of public interest in terms of the science that comes out of astrophysical assets. So this benefits the platform, and the public has a large amount of interest in planetary science using these kinds of astrophysical telescopes. So we went about the investigation by trying to break down the scientific investigations and technical investigations into those two groups. The scientific investigations tried to identify the compelling subjects of study, match them up with the appropriate platforms and unique capabilities of those platforms, and then that may be planned or suggested, and then identify the range of the spacecraft and payload criteria that would actually, keeping this in mind, that would actually span all of the populations within the solar system that we'd like to study. With all of that in the mix, we wanted to identify, in technical terms, the gaps in instrumentation and spacecraft architecture that were realized in previous generation platforms, and then that affected the planetary science capabilities, observing capabilities. You want to invest the trade spaces of these technical desirables in terms of bridging the gaps, and then weigh them according to costs and come up with priorities with all of those in the mix. These are just some examples of the capabilities and science drivers, like looking for the source of main belt comet activity, analyzing giant planet aurorae and atmospheric dynamics, looking for Planet 9 and so forth. And then some other examples of technical capabilities, including, of course, non-sidereal tracking, but also things like visiting cadence and rapid readout, things that may not typically come up to our first thoughts in terms of enhancement capabilities. So these are just some of the topics. So of course, probably the highest priority for capabilities to facilitate planetary science with astrophysical assets are non-sidereal tracking capabilities. Basically, if you can go, the tracking capabilities are necessary in terms of realizing the full potential of the astrophysical assets, bringing them to bear on moving targets. So now those may be limited by the specifics of the platform, telescope size, settle times, differential tracking capabilities, and so on and so forth. And that must be considered in the balance. But if you can go to someplace, and if you can go to a particular target on the sky and slew there, you have probably pretty much the capability of, if not in the hardware, if not in the software, to implement some kind of non-sidereal tracking. And failure to actually accommodate this capability really impacts the science that you can achieve in terms of characterizing the bodies, the targeted science that you can achieve. This is not necessarily applied to across the board, for example, passive survey strategies or large fields of view with coarse pixel resolution and so on and so forth. But generally, if you have a characterizing instrument like an IFS or something, you would want to have non-sidereal tracking to utilize it for planetary objects. Okay, some other categories include dynamic range. Observations of most objects can benefit and make use of large dynamic range in combination with increased sensitivities. One way to actually help this is a couple rapid readout with low noise in detectors and averaging over OADs for brief exposures that would avoid saturation. But rapid sampling in and of itself, as we just saw in one example with occultations, but also with events, time-critical events like neutral events and other time domain astronomy and solar system science that requires high sampling. Those are methods that have led to some key discoveries in planetary science in the past and should be facilitated on these platforms. Large fields of view can, of course, allow us to take large assays of statistical meaningful samples of objects, particular populations within the solar system. But limitations in terms of the field of regard, the range of elongations that may be viewed by a telescope, can especially impact planetary science observations, since they are usually of some associated time domain and are linked to different the objects. You might want to sample the objects throughout different orbital phases and other times. And so really a highly restricted field of regard really limits limits the observations to more or less serendipitous coincidence of a particular body passing within the field of the sun. Another set of major capabilities involves scheduling and ground-based data or ground data systems and mission operation systems. Basically, allowing all of the data that is important to solar system observations, making sure that that makes it into the data products and in planetary friendly form, planetary observation friendly form. Those are key, otherwise the housekeeping data may be eventually buried or lost over time. And then owing to, and then also keeping individual images which are full of reference objects, including astrometric reference objects and photometric reference objects in the background, and also in order to facilitate sufficient astrometry, understanding where the platform is, accurate station keeping is key. So these are just highlights of some of the capabilities that we've actually covered in the white paper, but it's important to note that even small considerations and minor adaptations can make the difference between successful planetary science programs with these platforms. The planetary science enabling capabilities should be considered early in the design and move forward with the implementation of the design. And flexibility in terms of marginal alterations like bandpass and with filters, or extending the wavelength slightly in terms of spectral coverage should also be seriously considered. And for surveys and other population studies, looking at the appropriate cadence to actually constrain the orbit should also be considered. So that is basically a rough summary of the white paper, and I'm happy to take questions.
Questions either in the room or online?
Hungry for lunch.
Yeah, so we are going to adjourn for lunch, which we will reconvene